Hello, and welcome to ThermoChemistry Notes, calculating delta H through bond energies. These will go with your 5A notes in the section labeled bond energies, and you will also need out your green reference sheet that'll have tables and maybe like 2 tables on it, or 3 tables. And it's the thermochemistry data charts. It's the one that has the bond energies on it. Okay, so you want to get those out now so you're ready to do your problems. All right, so this is the information from your notes. So one of the most important concepts to take away from this, so not just that it's a calculation, it takes energy to break a bond. So that is going to be your endothermic component, which will be breaking up your reactants, right? Because that's what you have to break in order to have room for new bonds. Okay, so in net total, you're going to break some of your reactant bonds in most reactions, not all, but most. And the energy is released when a bond is formed. So that's your exothermic component, and that's going to be your products. That's the bonds that you make, that you get out of the reaction. So in most reactions, there's some component that's endo and there's some component that's exo. So determining whether a reaction is overall exo or overall endo depends on which of the values is greater. Did it take more energy to break the bonds, or did it release more energy to form the bonds? And whichever one of those numbers, absolute value, is greater, will determine whether the overall reaction is endothermic or exothermic. All right, so, all right. So this is one of the ways that we can solve for delta H of a reaction by counting the total bonds of reactants and products, and then adding them up or subtracting them depending on which method that you're using. We're taking into account all of the bonds that are broken and all of the bonds that are formed, and making sure that we have the correct sign for each one of those. So some of the other ways you can solve for delta H would be Hess's law, standard enthalpy of formation, energy diagrams, and you can use calorimetry. So this is one way which you can do it. One of the things you have to be careful of, this method of solving for it really looks the same as standard enthalpy formation. And so you have to recognize a few differences between them. One of the biggest is that elements, such as diatomic elements, are not going to be zero if they have a intramolecular bond. So we're referring to bonds here, we're referring to intramolecular bonds. None of these have IMFs. So there are going to be no IMFs in bond energy calculations. If it has IMFs, this method won't take those IMFs into account. So you'd have to use it in a combination with another method. All right, so there are two strategies that you can solve this. Delta H of reaction equals the sum of the products minus the sum of the reactants. If you're going to use this method, you have to take your bond energy table, which all the values are listed as positive, and make them negative, because these represent the formation of bonds. The formations of bonds is always negative, and so that's how the logic that we're using to get the signs to work out. So you have to put a negative sign on the entire table. The other way that you can do this is you can add the total bond energy needed to break the bonds into reactants, and that gets a positive value. And then add the total bond energy released when the product is formed and give that a negative value. And you can just add the two of those together. I'm going to use method number one when I solve this. There's nothing wrong with method two. And personally, when I solve them, I actually do use method two. In terms of remembering how to solve it and problem solving through with some of these ways to calculate delta H, sometimes it's a little bit easier to do products minus reactants because that's when we already solved them. Okay. Be careful when you're reading the bond energy table because double and triple bonds are not the same as single bonds. On the AP test, they're not going to give you a giant table. They'll give you a small table and you'll pull values off of it. But you still have to be careful to know that the higher the bond, this should say the higher the bond, or the higher the energy of that bond. Okay, so that's very important. The higher the bond order, the higher the energy of the bond. So a triple bond will have more energy than a double and a single, respectively. Okay. So you have to also take into account the number of bonds in this case. So this is where it really differs from standard enthalpies of formation because you have to count the bonds. You're not just counting how many of each compound you have, but how many of each bond there is, and how many are in the coefficients of the balanced chemical equation. And one of the major limitations to this method is that it only accounts for intramolecular bonds. We mentioned this before, and no IMFs. Therefore, you can only solve for gases, or you'd have to use some sort of other method. So we're going to go ahead and do a practice problem. It's the one in your notes. Okay, so now we have a problem here. It's also in your notes. Complete combustion of so C2, it's a little bit smaller. Coefficients C6 plus oxygen is required for combustion. Balance this. Fraction. The only issue with it here is that it makes some of our calculations a little bit more complicated. So I would go ahead and just double everything. So this would become 2. This would become, now this would become 7. This would be 4. And this would be, wait, that's a 6. And that would be, oh, 6. Just make sure if you're doubling one thing, you're doubling everything. And I'm going to come down here and just erase this to give ourselves. All right. All right. So now we have a balanced chemical equation. And normally you would draw the structural formulas. I drew them for you here, but make sure you practice in the example, drawing them for yourself. You'll need to know how to do those structural matrices. So now what we need to do is we need to take each one of these compounds and we need to add up how many bonds in total are in them and what are the energies. So if we look at ethane, we have CH bonds and we have 1, 2, 3, 4, 5, 6 of those. And when we look on the chart, 6 times C is negative, because remember we had to make the whole table negative, negative 6, 6 times negative 4, 1, 3. All right, so now we're going to this next one here. Okay, so in the same compound, we don't just have CH, we also have one CC bond. Okay, so we also have to account for that. And that's one of the things to be really careful with organic molecules is that you will sometimes have more than one type of bond and you have to account for that. So for this, we only have one of them joining the 2 carbons together, and this is negative 346. So what we're going to go ahead and do right now is we're going to add this entire thing together. Because that will represent the entire molecule. What we have not taken into account yet is the coefficient out front. We'll do that at the end. So we have 6 times negative 4, 1, 3 plus 1 of the negative 4. And we get negative 2,824. All right, so now we're going to come over to the next one, and we have oxygen. That's our other reactant. So for oxygen, we have a double bond. So we have O double bond, and that's the only bond we have. So we just look this one up on the table, and this one is negative. And be careful with this because it's a double bond. You have to go to the bottom. Negative 498. Okay, so there's that. All right, let's go to the next one. CO2 has two double bonds, one here and one here. So one here, one here. And so we're going to have C double bond O. And that value is two of them, negative 732. That's a 3. Not a very good 3. All right. 2 times negative 7. Negative 1464. Okay. And then we're going to come to water. So water has two single bonded hydrogen oxygen. And so we're going to say 2 times, because there's two of them, one of them right here and one of them right here. And so we look up, this one we do on the top, because it's a single bond. It's a negative, because remember we have to make everything a negative. Okay, negative 296. So now we have the values for each one of the molecules. Now we just need to add them together to get the value for the whole reaction. So we're going to say, okay, let's do we always do products. H equals product. And it has a sum, but it's just easier to write this way. So our products are going to equal, okay. So our first product is over here. So we have got, and this is where we have to be careful. We have to take into account these coefficients, so the 4 and the 6. So we'll say, okay, 4 times negative 1, 4, 6, 4. So that's your 4 carbon dioxides plus your 6 waters, and water we calculate to be 962. Close parentheses. Okay. So this would be our total products. Minus, we're putting brackets to keep ourselves organized between products and reactants. We have 2 times negative 2824 plus a negative, let's see, we have 7 of these, negative 498. And now it's just a matter of putting it into the calculator correctly. Okay, and so I plug this into the calculator. And so overall, this is negative 2278. And our units here are going to be kilojoules per mole. And so overall, this reaction, it tells us that it is exothermic, which makes sense because this is a combustion reaction. We know it releases heat energy because it gets hot. And we could compare this to other methods of calculating delta H of a reaction, like standard enthalpies of formation, or some sort of Hess's law type problem. And so this would be our overall value. And if they ask you for just the products or just the reactants, you could add up one of the sides. Sometimes they'll ask you for, what's the total value for the products and what's the total value for the reactants, and then you could subtract the two and get your values. So you have plenty of practice problems to do on the I think it's thermo number 2 practice problems or your review sheet, and you can try these out for yourselves.